Hey everybody, and welcome back. Today we are going to be doing something a little bit different than normal. We're going to be starting part one of a three-part little mini-series we're doing here to try to help everybody better understand some of the strategy that goes into lineup construction. I mean, obviously you want to have your prediction algorithm give you the best lineup possible, right? And that's ideal. Everybody wants to have the best lineup physically possible for that slate. However, it is remarkably unlikely that you will have the optimal lineup for the night. It is possible. It will happen, probably, eventually. But the odds of that happening are very low. So what you want to be doing is putting yourself in the best position to give yourself the highest probability of winning for that contest. And I'm not going to read through all of this here on the video. If you would like to really dive in and read through all of this, feel free to check out the blog post. This is what the blog post will be posted. This exact Jupyter Notebook file is what will drive the blog post itself. So all of this text will be there. But basically, you've got two general types of contests. You've got GPPs, or the big money-making tournaments where you see all the big flashy headlines, win $1 million, get first place, yada, yada, yada. You have your cash games. Within each of those, there's going to be some other little subsets that we're not going to get into for the purpose of this video because it just gets a little too complex. This is supposed to be a very basic introduction here. You want to pay attention to the cash payout structure of your tournaments. So for GPPs, the big tournaments, the vast majority of that money that gets paid out is for like the top 5, the top 3, the top 10 spots in the tournament. So if you're not getting in those top 10 out of 500,000, 800,000, a million people, you might still turn a profit, but it's going to be minimal. You can do a lot better for the most part, depending on how you make your lineup. Alternatively, you have cash games where it doesn't matter. It'll be like the top half of the people win, or like 100 people enter, the top 45 win, right? That way they can get their rake still, and the top half left over after that are going to cash out. So in a cash game, if you get first place in a cash game, you get the same amount of money back as the very last person to cash. Okay? You are not rewarded for being the best. You just need to beat half the field. And it's all the same after GPPs. You want to be in that top 3, top 5, top 10. You are overwhelmingly incentivized to be in that top few. You get one game where you're the top 3 in a big payout GPP, and that can cover losses for a very, very long time. Or if you don't have a lot of losses, that's just a lot of cash in your pocket. All profit. Beautiful. But depending on what type of game you are entering, you'll want to change how you construct your lineup. Because if you're playing a cash game, you're going to want to be a little safer, right? You just need to beat half the other people. You may be comfortable with a chalkier play, someone that everyone's going to be picking, because you're not going to be rewarded for being the contrarian here, right? If everybody's picking Kevin Durant and you pick Jeff Green, you're probably going to be on the losing end of that battle, right? Now there will be a night where Jeff Green pops off and scores 35 points and Kevin Durant goes down with an injury in the first quarter, and if you're in a GPP with that lineup, you're sitting pretty. In a cash game, though, it's much less likely to happen. The scenario is equally likely to happen, but you'll be rewarded more in the GPP because the cash game, if everyone else has Durant, then everyone else is handicapped. So if you have Durant too, you're still on the same playing field as everyone else, right? You're not at a disadvantage. Where people that do very well in GPPs, they will put you at a disadvantage because they will be playing specifically contrarian lineups, or at least contrarian players with a more standard lineup, so that if it is one of those one nights where it pops off, that's going to be the optimal for them, and they win. It's very good. So something that you can do to kind of differentiate what types of players you want to use when is going to be identifying floors and ceilings for players. So I'm sure if you've been around the sports world at all, you've heard a player get called a high floor player or a high ceiling player. And you can be both. What that means is a floor is going to represent like your worst night, your worst consistent night. Anybody can have just a shit game, right? But consistently, this is your low point. Players with a high floor are going to be players that, even on a bad night, still perform at a pretty high level and give you what you... Players like Kevin Durant, LeBron James, Russell Westbrook, really James Harden, really high usage, high utilization players, playing through injuries, so maybe we take LeBron and KD off that list. But you get what I'm saying. Like you can be very confident that no matter what happens, they're going to get you at least this many points. Players with the really high ceilings are going to be the ones that don't necessarily have that consistency, and they may not even have be consistent high performers, but they do have those big games. They are in a position where they will thrive when the conditions are met. So that you want to think of more your role players, the matchup dependent players. Those types of guys can be very high ceiling, and they're not going to be popular picks because they're not consistent. So the average person coming in, you look at fantasy points per game, last 3, 5, 10 games, whatever they show you on an old DraftKings bubble or FanDuel bubble, and you make your pick there. If they see a low average recently, or just a low average in general, they're probably going to shy away from you and think you're overpriced. However, if you know they're a high ceiling player and they have that prime matchup coming in, or there's a pretty good chance that the player ahead of them is out with an injury or sitting and they're going to get more playtime than normal, and when they get more playtime, they perform, those are the type of situations you want. First, we're going to look at how we can mathematically calculate floors and ceilings for players. And to do that, we're going to be using what's called the standard deviation. Now, I know that math class was a very long time for a lot of folks, and there's nothing wrong with that. The standard deviation is not that complex. It's going to be pretty simple. Here's your equation for it. I kind of wrote it out in English. It's going to be the square root of the sum. That's what this little sigma is. It means we're summing up everything here. And then that summed value, which just means you're adding them all up together, is going to be divided by our capital N, which is our total number of samples. So our little curly X is going to be the data value we're looking at. So that would be fantasy points for each game. This little goofy looking U is going to be our mean, or the average over the set. So that would be their fantasy points per game for the season. So we would take every single game, we'd subtract the mean from that point total. So that could be a negative number if it's less than the average. Those bars mean we're taking the absolute value, which, to be honest, doesn't even matter because we're squaring it anyways, and squaring a negative number is still the same thing as a positive number. So we do that. We store our little number here. We do it for the next game, and the next game, and the next game, and the next game. We add that up for all of the games. So what we're calculating is basically how far off the player was from their average that night, and then multiplying it by itself is all we're doing. And we take that, and we're dividing it by the total number of samples. So if you know how to calculate an average, you just sum all of your items and divide by however many there are. So in a way, we're kind of taking the average of how far off of their average that they are, if that makes sense. I think it does, but I do a lot of math. So if that's not making sense and you aren't as fluent in math, or it's just been a long time and you're a little rusty, let me know down in the comments and I'll do my best to explain it better. Maybe with a different example, something more relevant to you that would make sense, but let me know. I'm more than happy to dive into it a little bit deeper. So again, this is just kind of breaking it down step by step, like first data point minus the mean squared plus a second data point minus the mean squared plus a third data point, ... so on and so forth. We're actually going to do some calculations here, get into it a little bit. This is what we're going to need to import. We're going to need numpy matplotlib.pyplot because we're going to do a little bit of graphing, and then scipy.stats. We're going to do a normal distribution at some point. I don't know if we get to it in this video or not. Surprisingly, having not put out a video in so long, I made this quite some time ago and just have not had time to record. So I'm not really sure what is at the bottom of this Jupyter notebook, so we'll find out together. So let's go ahead and import our packages. And what we're going to do here is define x's and y's, just generic x's and y's. We're going to use a numpy, a range, pretty self-explanatory on the tool we're using. And what this is saying is we want it to go from -4 to 4 at increments of 0.1. So that's going to give me -4, -3.9, -3.8, -3.7, all the way up to 3.7, 3.8, 3.9, and 4. Okay? And then for the y, we want a normal distribution And if you have no idea what that means, don't panic, we will get to it. A normal distribution of x values, and all this is, I don't have it written out with the parameters, but 0 is going to be the mean and 1 is going to be the standard deviation. That's all we're saying there, is that we're predefining the mean and the standard deviation for this arbitrary data set that we are creating for the purpose of this example. Normally, you have your data and you calculate the mean and the standard deviation from it. But since we are generating it, I'm just going to show you here. So x's, you can see I have my array 3.9, 3.8, 3.7, down to 3.78 and 9 in the positive. And again, since we are using a Python range, we stop 1 before the final value, so we don't actually get to 4, because that is the exclusive bound. Inclusive, I might have spaded that up. And then our y is going to be those y values for the corresponding x values, okay? And that's because we know we're starting at -4, we're going to 4 with the x's, and then for the y's, we want for the x's in a normal distribution. That's just going to put it in a bell curve, centered at 0 with the standard distribution of 1. So I'm just doing a little bit of explaining here. What we're going to do next is we're actually going to create a figure, and we're going to plot that x-y relationship with just just plot those points. So if you've never used matplotlib.plt before, I guess it's pyplot imported as, matplotlib.pyplot imported as plt. That's just kind of like pandas is pd, numpy is np. Just kind of industry standard for how to reference it. You don't have to do it that way. Completely up to you. All I'm doing here is defining a figure, and I did this a little more complicated than you need to. If we were doing multiple plots, multiple different graphs within one pyplot object, that's why I'd use subplots, because I've used that before, where you can define, your different figures, and if you wanted, to graph x's and y's here, k's and z's here, b's and c's there, but you want it all on one matplot object, you would use subplot 1, 2, 3. Don't worry about that. If you write it like this, it'll work. Defining the size, I want it to be 9 by 6, and then I'm just saying for that plot, I'm plotting x, y. So if we plot it, we got this nice line, and again, -4 to almost 4. And this is where we kind of get into the bell curve. You'll see that this is centered at 0. That's going to be the mean. So if we add, basically what that means is pretty much everything, every one from this side minus one from that side, like there's a corresponding value on the other side. So when you add them all together, the negative and the positive, it's going to keep hitting 0, and 0 divided by a number is 0. And the other part we defined, if you remember, is that the standard deviation will be 1. Okay? Now that really means nothing to us right now. But what I'm going to do here, and I'm not going to spend a whole lot of time going into the graphing of this, because that's not the point of this. The point is to get these visualizations to kind of take a look at it. So what I've done is I drew a line, a vertical line at x equals 0, just to kind of visualize the mean. This is right where it is, right here. Because I'm terrible at visualizing things, so I need it on the screen to look at. Then what I've done is I have told pyplot to fill underneath the curve from x equals -1 to x equals 0. So we're filling up that area. However, as you can see, there's a gap here, because our x-axis is actually above the bottom of the graph. I don't like that. So I do change that next. I go ahead and drop it down here, because that looks better to me, coming from a mathematical background where you're like calculating area under the curve and such. I like having a boundary there. It looks nicer, I think. So all I've done there was define the y limit for the bottom to be 0, and I think I moved the y limit on the top a little bit too, just to give us a little more room up there. So that's all I've done. I've defined the x fill and the y fill boundaries, and I told it to fill between that area using the color blue. Alpha is going to be the transparency or the opaqueness, so nothing crazy there. But this is a bell curve, and with a standard deviation of 1, that means I have shaded in everything that falls within minus 1 standard deviation of the mean. Okay, and as you can see, that's a pretty big chunk of the area underneath this curve. And what the area underneath the curve represents are the possible outcomes that fall within that area. Okay, so we're going to go ahead and build out the bell curve, and this may start to look familiar to you from school. However, normally you wouldn't have the lines up top, but I am way too lazy to put in bounds on those vertical lines as well, because then I have to calculate the y value for that x point, and no thanks. So we're just going to have the lines going from top to bottom. And as you can see, we've broken it off, 0 to 1 standard deviation, 2 standard deviations, 3 standard deviations, 4, -1, -2, -3, -4. Okay. And now that we have it visualized, we're going to start getting into how you can use the standard deviation. And I went ahead and visualized this here with different colors. So if you want to go through and look at this, you're going to see I did the exact same thing as up here. I just did it for each section. No, don't move it. Don't do that. I just did it for each section, and then did a different color for each section. That's all. Nothing crazy. But I wanted to visualize how we're going to be breaking this up, because the bell curve is used to calculate probabilities of events occurring. So the area under the curve is basically going to represent the probability of an event occurring within that section. And the way you want to look at this, and since it's a bell curve, the numbers are nice and even and easy to work with, which is why we're using a bell curve and not real life data. Real life data is not quite as clean, as it never is. But basically, if you are within 1 standard deviation of the mean, there is a 68% chance of that happening. So if you think about it, consistent players would have a lower standard deviation, because that means that 68%, let's say you average 30 fantasy points per game, okay? You have a standard deviation of 10. That means that 34% of the time, you're going to be between 30 and 40. 34% of the time, you're going to be between 20 and 30. And 68% of the time, you're going to be between 20 and 40. Now, that's a pretty big gap, right? So let's look at the same player, but let's say he has a standard deviation of 5 points. Still averages 30. That means that 34% of the time, he's going to be between 30 and 35. Okay, which isn't up to that 40 mark, but you have a much better idea of what you're getting. 34% of the time, he's going to be between 25 and 30. Again, that's better. It's not quite as low as 20, so you can feel much better about that. That means 68% of the time, you're going to be between 25 and 35 points. I can live with those odds. Okay, I can feel pretty good about that player scoring within that range. And if that is an acceptable range for my lineup, especially for a cash game, if I'm looking for high floors, if I can guarantee every player on my team scores between 25 and 35 points, that's not bad, That's not bad at all. And it keeps going on, so on and so forth, For our player that scores 30 with a standard deviation of 10, there's a 14% chance he's going to score between 1 and 2 standard deviations away from the mean. So that would put him between 40 and 50 points, a 2% chance of scoring between 50 and 60, and a 0.1% chance of scoring between 60 and 70. And that again comes backwards the other way. You have a 14% chance of scoring between 10 and 20, a 2% chance of scoring between 0 and 10, and a 0.1 chance of scoring negative points, or more precisely between 0 and -10. So a way to look at that, your average performance is going to fall on either side of the mean within 1 standard deviation of that mean. That's just kind of the general accepted average performance. Your good performances are going to be more than 1 standard deviation past the mean in the positive direction, and a poor performance is going to be more than 1 standard deviation below your mean, okay? So if you're looking for a high ceiling player, you may look for a player that has a higher standard deviation, because that means they're less consistent, but that means when you're looking at this 14% marker, depending on what their average is, it could be significantly higher, right? So if you're gambling on 14% chance of them scoring in this range anyways, or 16.1 if you want to keep going all the way up, you're going to want to gamble on who's scoring more points if you fall within this category, okay? Because if either way you have a 16.1% chance of scoring 40 points or 55 points, I'd rather take the player that has the same odds of scoring 55, right? And this, again, all of this is occurring in a vacuum where everything is driven by the bell curve, and obviously that's not real life. You have matchups, You have defensive schemes, you have injuries, you have new rotations, you have trades, new teams, new coaches, drafts, new players that got to play with. It might take a little while to mesh and get on the same page. So things will vary pretty substantially, but this is going to be the basics of how we're going to be trying to figure out who is a high floor and who is a high ceiling player. Who do I want to play in cash games? Who do I want to focus on in big GPP tournaments? And that's pretty much the gist of it for today. Again, if you have any questions about standard deviation or floors and ceilings or the bell curve in general, feel free to reach out. Drop a line in the comments. It's probably the easiest way. Obviously, on the Patreon, you can hit me up on Discord or on the Patreon page itself. That's perfectly fine. Speaking of Patreon, again, always huge thank you to everybody in the Patreon. I know I have been MIA as of late, but we're getting back into it, getting back in the swing of things. And we got a whole lot planned and a lot coming out in the near future. So this is part 1 of our 3-part mini-series, Floors and Ceilings. Next time, we're going to start actually looking at some NBA stuff and how we can relate it. In part 3, we're just going to keep getting, stacking, getting more advanced, getting more in-depth, getting more functional data we can use. So with that, I wish you all a wonderful day, evening, morning, wherever you happen to be in the world. Have a good one. See ya. Thank you.